on my face. I'm a scientist at the Space Science and Engineering Center, where Tim is, who gave the satellite talk. I work for SIMS, which is sort of part of this, sort of a subunit. And yes, my research is on, essentially it's basic research on supercells. And I'm using supercomputers to simulate them. What that means is we essentially take very sophisticated models that, to the best of our ability, use the laws of physics to basically forecast the future of the atmosphere. This is done with our climate models. This is done with all sorts of models in the world. It can be done on tornadoes as well, and supercells. So I'll talk to you today about some of this work, and I'm also very interested in getting these storms to look like the real storms. What I mean by that is I'm able to use techniques of visualization that give us insight, that peer into the storm, peel layers off of the storm, and look into it. So the basic questions I'm exploring here are, how do some tornadoes form in supercells in the first place? Okay, it's a very difficult issue. We've tried different proxies for tornadoes. We look at TVS signatures. We look at these new tornado debris signatures, which are excellent. In this case, it's something that you're seeing after the fact. We'd like to be able to predict these better. We'd like to be able to look at a radar image or maybe a forecast and say, where are the storms going to produce tornadoes and where are the storms not going to produce tornadoes? So these are outstanding questions in the field of mesoscale meteorology. So unlike many folks who do field work, I'm almost entirely inside the computer. That's just kind of what scratches my itch. I enjoy programming. I've enjoyed programming since I was in high school. When I was very young, in Massachusetts actually, if you want to talk about a real storm, October 3rd, 1979. Anybody remember that one?
I was there.
Windsor Locks.
Yeah.
I lived in Ludlow, or Feeding Hills at the time, just north of the Connecticut border in the Connecticut River Valley. That storm basically dissipated over my house, or very, very much in the area. I was in 6th grade, and I remember kids doing posters about the tornado and drawing pictures of little swirly things. A few years earlier, my house got hit by lightning. And this is again in Western Mass. Not exactly a hotbed of severe weather, but it seemed to find me. So I got interested in this, but eventually I met computers, and then it was game over, because I knew I wanted to do computer work, and then when I came to college, I discovered you can take computers and do weather. Oh, I'm right where I want to be. Okay, so over the course of many years, I got more interested in computing, and then started to do work with parallel computing, which requires supercomputers, and when you basically, it's the nice way of divide and conquer. You know, we're in Wisconsin. Divide and conquer has been used in some ways to be like a bad thing. But when it tries solving a problem on a supercomputer, essentially you're breaking it up into lots of pieces, but what you're conquering is the physical problem. You can do things with supercomputers that you simply cannot do with standard computers. So you're going to see a whole lot of really cool looking animations. These are just volume renderings or visualizations of the data on the computer. We're getting to the point now, when I say we, I mean my research team, of answering questions more quantitatively and publishing in journals and things like that. Why are we studying these high-end storms? So I'm interested in EF5, EF4s, preferably the ones that are on the ground for a long time. I can count on both hands. The last maybe 30 years, we've had maybe 10 of those. If you're from Wisconsin, obviously, and you know about the Barneveld tornado in 1983, F5 wiped out the entire town. You go on west and you drive by that town, and none of the houses are older than 35, 40 years. So this does happen in Wisconsin. So it's kind of obvious why I want to study these storms, but one thing that is not obvious is that we're really bad at forecasting them. We've heard about all sorts of amazing technological breakthroughs in observational meteorology. We're on the cusp of this. We're on the cusp, I think, of being able to say things like, this supercell is probably just going to, maybe produce a very weak tornado like the one on 151 and be done. That wasn't even a supercell, by the way. But, maybe it's going to be a long track EF5. And that's the kind of forecast we need to be able to make, because those are the ones that do just the most devastating damage. So I'm looking at the top end tornadoes. I'm trying only to study those. I'm not trying to say that what I'm doing applies to all supercells and all tornadoes. No, I'm only looking for these high-end EF5 long-track storms. So how do you do this? I'm using a cloud model, which is a computer program that essentially follows the laws of physics and forecasts the next few seconds in time, or fraction of a second in time. Using this process, we can watch the cloud grow like we're growing maybe you're in a laboratory growing something from a culture. In this case, the computer is the laboratory and you're growing a storm. So you need, in order to do this the way I'm doing it, you need to sample the atmosphere pretty faithfully. In this case, we didn't use a Rhea balloon launch to initialize the model with the atmosphere. We used another model forecast to initialize the atmosphere. So it's models all the way down in a way. But the truth is, what we feed those models is observations. Rhea, infrared, satellite imagery, all the remote sensing techniques get fed into what's called an assimilation process that then gets into our forecast model. So it's not that important, but what is important is that we try to simulate a real event, or at least to the best of our ability. So this isn't just a theoretical supercell. This is trying to be as close to 24 May 2011, EF5 that occurred in El Reno, as possible. Okay, so what do you need to do this? You need a good, garbage in, garbage out. You need good input. You need a really big supercomputer. The computer we're using is called Blue Waters. It is sponsored by the National Science Foundation, so this is also, thank you, coming from all of our tax dollars. It has over 360,000, what you might say, individual pieces or floating point compute cores. The way these supercomputers work is they're basically multi-core nodes all hooked together with a really fast network. So one piece of Blue Waters is 16 floating point cores, and you have 20,000 of them or more, and then you can do some really interesting things. When you start talking about petabytes, you're talking about big data. And one way of looking at it, the problem I'm trying to solve is indeed a big data problem at its most basic. I've got a lot of data, and I'm trying to understand what's going on inside that data. Much of the work that I have done has been with getting, fine-tuning the model so that I could save data enough to make these cool pictures and stuff. Because from my perspective, I've always been very interested in visualization, in bringing the computer simulations to life. And to me, that is the first step at trying to understand what's going on. It's a very important step. You need a bit of luck, just like going on a chase. When I fire up a job on a supercomputer, it might not produce a tornado. I'll probably get a supercell, but I might not get a tornado, just like when you go out chasing.